Another implicit assumption we have made so far is that all the actions we execute are instantaneous. A more realistic approach is to assume that our actions are durative, which means they take time. So every action we consider takes a known amount of time, and every action has a start time point and a finish time point. Now, we have already seen that the A-star algorithm takes the action cost into account, so it can search actions that have a given cost, and one approach is simply to assign the time they take as the cost of the action. And in fact, the FF planner we have seen last week has been extended in this way to take time into account. A different approach that is often used in conjunction with partial plans, and specifically in conjunction with HTN planning, is to use a temporal constraint manager as a plugin component to the planner. And there are two flavors of it that are quite well known. The first one is called the time point network. A time point network simply associates all the time points in a given plan. So we have a start and a finish time point for each action, and we can assert relations that must hold between these different time points. What we get is a network like this one here, where we have 6 time points, and they are related by these different relations that we see on the edges in this network here. The good news is that the consistency of time point networks can be checked in polynomial time. A more complex approach that has been proposed is an interval algebra. So now we're relating not time points to each other, but the intervals that correspond to the action execution. So if we have an interval I1 and an interval I2, we can say that one interval must be before the other, and we use this relation b here to express this. What this means is that the end time point of the first action must be genuinely before the beginning of the next action. Similarly, we have other relations like meets, where these need to be at the same time point, or overlaps, where one comes after the other, and start, during, and finish are 3 more relations we have here. As it turns out, the interval algebra is more expressive than time point networks, so there are constraints you can express in the interval algebra that you can't express in time point networks. But on the downside, checking consistency in an interval network takes exponential time. One of the things that all the approaches we've looked at so far have in common is that they don't learn. So if we give them a planning problem to solve, they search or use whatever technique to solve this problem and come up with a solution. If we give them the same problem again, it'll take exactly the same amount of time and resources to solve this problem. Or if we give it a similar problem, the planner cannot take anything from that similar problem to the new problem and try to solve it better. So one approach was to try to apply learning to planning to somehow improve the performance of the planner over time. So the general idea is we let the planner solve a series of similar planning problems. Then we somehow analyze what the planner has been doing during the problem-solving process. And the result of this analysis should be something that we can feed back into the planning process to make the planner more efficient on similar problems. That is the general idea, and that is what you would expect from human planners when they start solving similar planning problems. They would get better over time. And there are a number of ways in which this learning can be done. Here are 2 of them. One is the learning of macro operations. So our planning problem contains already a set of operators that we can use to solve that problem, but we can increase that set with macro operations that perform larger steps in our search space. Of course, this is somehow similar to HTN planning, where we also had more abstract methods that summarize what needs to be done at a lower level. Another approach that has been tried is learning search control knowledge. So during the search, we often encounter states that have the same F value. So the heuristic doesn't help us to distinguish these states from each other. And search control knowledge helps us to decide which path to explore next in our search space. Another assumption we have made so far is that we're dealing with a single planner that has control over all the agents that are executing the plan. So in our dogworker robot domain, when we were planning, we assumed that the robots and the cranes during plan execution would do as they are told by the single planner. However, in multi-agent planning, this is not the case. So we no longer assume that we have a single agent that is in control of all the other agents. Of course, this complicates the problem significantly, and there are a number of flavors in which this problem can be developed. For example, if the agents we are dealing with have different beliefs about the world state they are in, then this becomes a quite different type of planning problem. Or we can have planning problems where all the agents have all the capabilities, can execute all the operators that are available, or agents have different capabilities. So some operators can only be executed by certain agents. Again, we've seen this in the dogworker robot domain, where the robots can transport the containers and the cranes can load the containers. And of course, cranes at different locations can only load the containers that are at their locations. Another aspect of multi-agent planning are the goals. So we can have agents with joint goals, so that all the agents want to achieve the same goal, or they can have individual goals. And this becomes worse when the individual goals are actually conflicting or contradictory. In this case, the agent can be adversaries, like in a game of chess. So you can see there's a whole range of multi-agent planning problems. And another aspect that is somehow different is the problem of joint actions. So suppose you have a table with some objects on top of it, and if you lift just one side of the table, the objects will fall off. But if there are two agents that lift both sides of the table at the same time, then the objects will stay on the table because the table stays level. This is an example of what is called a joint action. It requires multiple agents to coordinate to execute that action. And a single agent alone cannot achieve the outcome of that joint action alone.